So mine, yes, you can see that the first of all, I'll just give a brief introduction about hyperspectral imaging because not everyone may know the background of the hyperspectral imaging. If given the generic image, we know that the image will be a spatial signal. We have a 2D signal, either in the color or in the grayscale. But that will be for the color image. We have the 3 channels. So that will be we show here is the actual electromagnetic the spectral here. We can see from the X-ray to UV to visible to infrared and microwave. That codes the whole the spectrum range there. The visible range, RGB, cover very short or very small portion of the spectral range there. Normally, it's about nearly 400 to something around 800 nanometers. But actually, if we talk about multiple spectral hyperspectral imaging, then we can cover much longer or larger the spectral range there. For example, multiple thread, we are talking about not 3 channels, but can be tens of channels. Typically, it can be sometimes less than 10, maybe 8 channels from the satellite remote sensing, or 16 or 32 channels. That be for some kind of snapshot cameras. And they can cover, I said, not only visible, but also can cover slightly near infrared and even go slightly further. If we talk about hyperspectral imaging, then it can be hundreds of the spectral channels. The hundreds of cover, some can cover the UV, visible band, and near infrared, short wave IR. They all together can be from UV can be 280 from them to nearly 380, nearly 400, and then from 400 to 2,500. So that's a very long spectral range. We show that a spectral signal here. Hyperspectral can then become a 3D structure. We have a 2D is a spatial domain. Another domain is the spectrum or the index of the bands. Just as shown here, the index of band for them can be from 0 to maybe 200 or whatever. We may have a kind of thousands of bands, depends on the applications. So we can then process data either pixel based. Each pixel will be a spectral vector that we call spectral profile there. Or we can check to process that one band by band. Each band would be a spectral image. Actually, it's a one dimension. It's a one channel grayscale image. So that would be just a one channel grayscale image. You can check that one channel by channel, or band by band. So altogether, this we call the 3D hypercube. The major motivation why we would like to have that one, it's just like Raman similarly, because it can help to characterize the object or the target of interest in a non-destructive way. Just like you scan the object, then you get to the spectral profile. Then we can tell about the coordinate spectral profile, can tell whether that's what kind of object is and what kind of property in terms of the chemical and the physical properties. The chemicals were chemical, for example, chemical compounds. If the change of a chemical compound, for example, the metal can be corroded, or if that's a physical one in terms of the temperature, moisture, and then can be extended to some other property. So this will be something very important for object detection or classification or recognition. This will give you one example. So that's the one of the hyperspectral image data called AVIRS is from the airborne system captured in 1992. That'll be from NASA. From NASA, that data set spatially is only 145 by 145 by 145 pixels. It's very small. The spatial resolution is about 20 to 30 meters. You can imagine it's 20, 30 meters. That's a very cool lower spatial resolution. But a spectral covers 400 to 2,500. Then we go to altogether. Actually, the original data set is about 224 bands. We only show 200 because the other 24 was thought to be very noisy, affected by the water and by the atmospheric effect there, because it is an optic sensor affected by the moisture in the air. So that would be the major reason. This shows us, for example, the three typical different objects, for example, the coins or soybeans or the woods, and how the spectrum looks like. Yeah, sometimes they are quite distinct from each other. Sometimes they are quite close, similar to each other. That shows actually we can use this information, try to tell people, so what kind of random mapping classes that would be, for example. So what will be here for each of the objects. We actually, the data has about 16 classes there. And we suppose that based on the spectrum, there should be within the class, if the object becomes the same class, it should be quite similar in the spectral domain. Or if we're in a different class, they should be quite different in the spectral domain. But this shows us it's actually not that straightforward. So sometimes the different classes can look quite similar. Sometimes the same, even the same class, for example here, ground truth define this is one class. But if we check about the object here, and that's a ground truth, and that's object you can see. The object itself, it contains a much more complicated pattern there, which means the pixels, at least the intensity are different. So that shows the kind of variations within the class. Yeah, so that will become some challenge in there. Because we have the intra-class variation that shown there, that mainly due to the environmental and optical noise, as well as the spectral mixing. And spectral mixing was mainly caused by, I said, it's about low spatial resolution. And also large volume of data, because of 3D structure, you can imagine, we can have to consider the X, Y, and then times the number of the bands there. So that's a whole volume of data. It's a 3D structure. Also, we have the Hooft phenomenon. So that will means we have insufficient samples in comparison to high dimensions of data. As I mentioned, this data can be 200 the dimension 200. But for some small classes, we only have maybe the samples less than 200. Then the coming to the question, if we would like to do a kind of a prediction model, for example, regression analysis, you have too many variables. But the problem is you have limited observed samples to solve the problem. Then that's why we have to do a kind of a dimension reduction. For example, using principal component analysis or use some more advanced technologies. Otherwise, it will be almost impossible. You can try to do the modeling using data. And we have actually developed a lot of as an algorithm for addressing this challenge. So that will be including one of the feature extraction. So how to get useful data featured from the spec data. One is called folded principal component analysis. So principal component analysis is quite a popular technology, but we actually just suggested a new technology which mainly to address the challenge is PCA is too noisy. PCA is noise sensitive. Or in other words, PCA is very noise sensitive. So if we apply the PCA directly to the spectral data, we can hardly get to the best results. That's why we propose that technology eventually can get we call local and global information and help to do the feature extraction there, followed by classification. And also we develop a single spectral analysis technology. We have that's a kind of technology actually used the major for time series prediction analysis. We take the spectral data as a time series and then apply that technology. Then also extend the technology to 2-dimension SSA, 3-dimension SSA, and also a few about the transfer domain SSA, plus some kind of fast implementation to improve the efficiency. So there will be more than 10 different variations technologies developed to improve the efficiency and also efficacy there. We also apply the joinless bilateral filter that's based on the plus the sparse learning, because the spectral data has a high redundancy here. So we can consider that kind of using a kind of a sparse representation-based approach, sparse learning-based approach. Of course, deep learning. Deep learning will focus on one is the spatial domain process and the spectral domain process, and also the combined together that we call spatial spectral or spectral spatial combined process. So then using that one, for example, using autoencoders, and also the kind of segmented autoencoders, similar like the technology we put to the PCA. And also we apply the called unsupervised band selection. As I mentioned, the hyperspectral imaging has a large number of the bands there that give the high dimension of the data there. How we can reduce the data, for example, if we apply the PCA, can reduce the dimension, but that means that the original data have just be transferred to the PCA domain. Another idea is band selection. Is just we have 200 bands. Can we actually select the most informative ones, for example, 20 bands, without significantly affect the results? So that will be the band selection. Of course, this is application driven, depends on the application, what you would like to be measured or to be checked, to be detected in the data. But we can use that unsupervised, which means given the data set, we do not use any ground truth information. We can start to model the problem using either the information theory based plus the they call discrete gravitational search. It's a kind of a smart search algorithm. And also we have the band clustering, how we can do the band clustering, build a tree structure, eventually identify which one will be most useful ones. And as I also mentioned, deep autoencoder based with the entropy constraints. So we developed also a number of technologies for band selection or based dimension reduction in this area. For image classification, that can be used for quality control and grading, detection of the disease and foreign matters within the data. For example, we want to detect some kind of disease of the fruits, or we want to detect foreign matters of the products. And this kind of application, I'll give you a number of examples to show how the AI spectral analysis can be combined to solve the real industry challenges here. Actually, on the nano mapping for this for remote sensing and disaster assessment, so that will be also for mainly for remote sensing. So in this area, we have published 100 plus articles and also complete more than 20 research projects and loads of the interesting applications. So that would be something I hope you will find is helpful. And just very brief mention for example, give an example of all the technology. For example, photo principal component analysis. This shows that given the data from the last in 1992, and then we apply the PC and photo the PCA. PCA, we get the first 10 components. We can find that most of the components are very noisy. If you apply the photo PCA, the 10 components remains to be very effective. Then if we use that 10 components for classification, you can see the traditional PCA gets result like this. If that will be, you can say 10 or 10 components, 20 or 30, 40, you can see the result was very poor when the number of the components is lower. And it will become much better when the components reach over 100, 120. Imagine that's only 200 bands. You only need 120 components to reach the result, similar like using the raw data for classification. That's the blue line is raw data. But what happens if we are using now photo principal column, that's a green one. You can see even use 10 bands, we get a much higher classification accuracy. If we got 20 components, it can overperform the raw data using all the bands. Then 30, 40, 50, it all becomes much more effective because the noise has been reduced. That's why it gives a much better performance, even with much reduced number of the components. But of course, if you increase the number of the components to be used, more noise channels, more noisy data will be included. Then the results tend to be similar to the raw data, like that. That shows exactly the potential, the greater the value to apply this technology for more effective feature extraction and data classification in spectral analysis. That's just one of the examples here. And another example we show is a two-dimensional signal spectral analysis. We use that one for non-carbon and again for this data set. Because that data I was mentioning, it had very low spatial resolution. If that's original one of the part, then if we apply the two-dimensional SSA, we can decompose the spectral data into 25 different components. Then that's the first component. That's the first 5, we add them together. That's the first 10, we add them together. Of course, if we add together all the 25 components, it will become exactly the same as the original one. But if we are using only the first components as a trained signal, it's a much smoother version of the original data. For classification, we can see the baseline using all the data is about 86.5. That's the classification accuracy. And then if you apply our technology, now become 97.5 nearly. So that will be about 11% of the improvement on top of that. That's a significant breakthrough if we compare with what's already there. Given that we use the same classifier, but just change over the feature. For example, we take this as a new feature rather than using raw data that give us much improved the performance there. That's as mentioned. I'm not going to cover all the technology we developed because that would be too lengthy. And I would like to give more about the applications we have done and how to apply this kind of data analysis and to different applications. Then our focus mainly actually will not give all the data or technical. So this just shows the publications. For example, that's will be application driven from the applied spectral groups, be the food chemistry, the computer agriculture, electronics in agriculture, triple transaction, industrial informatics, and instrument environment, all these things. And we also have the ones for data analysis, for example, knowledge-based system, pattern recognition, neural computing, and information fusion. And these are remote sensing related. The remote sensing, different remote sensing journals, some are the actual transactions, and some is on high level ones. So if you're interested, you can check my Google Scholar page. You can find quite a number of the technologies. The interesting why we use remote sensing, because remote sensing has been it's widely just focused and with some public available data sets widely acknowledged. We use that one actually to verify our methodologies in hyperspectral imaging analysis. So the application, as I mentioned, we have applied that one in a wide range of applications, including for the food quality analysis, the precision agriculture, the heritage arts, for example, the murals and the paintings, and pharmaceutical applications to apply to analyze the tablet and the effect there. The forensics, for them even detect the fingerprints and also detect some kind of UV signal can detect some blood samples as that. Automatic sorting the plastic, sorting the rice seeds that can be also in the agriculture related. Additive manufacturing, that's for a number of the application for the 3D printing of the components and the industrial automation as well. So other than recycling now I just quickly give that, now with technology, now came to some application. One of the interesting application we did is just, we were asked to see, can we actually use spectral image to tell people's, to use that one to estimate the shelf life of the baked products, such as the cakes. That can be vanilla cakes and chocolate cakes. Imagine when a cake was baked and they can put them in the shops for selling. We can imagine that can be for 1 week or 1 month or even longer. So how that can be evaluated. So normally, actually, they have the tasting panel, so a group of people can eat that one, and then give a kind of a ranking to see how good that one is. They feel, but that would be really, on one hand, a waste of money because you have to pay for someone to eat your cakes. On the other hand, the result could be very subjective. It depends on different people's feeling. And that would be you will expect the result can be nice, consistent. And on the other hand, you can imagine giving people the chance to always to taste the part of the cake, for example, has been there for maybe too excessive long data, for example, more than 30 days or more than 3 weeks. So it will be a little bit tricky. So that will be coming to a question, can we actually use the hyperspectral imaging, try to predict the shelf life of the cakes? We did that one using our spectral camera. For example, this is spectral. They show spectral from the day 1, day 5, day 8, day 9, after the data were, the cakes were baked. And then we show the result from the chocolate cake and also from the vanilla cake. The spectral is from nearly 380 nanometers to 1000 nanometers. That's what is visible to near infrared. It's not a much high quality spectral camera. And this is the result. Actually, using we did a kind of a dimension reduction followed by the regression analysis. We try to predict the quality index. So we can have the one taste the red one taste, which means the human experts, how they think about the quality. For example, when the cake was baked the first day, the quality is about 100% good. Yeah. And then after a few days, this will become down to nearly 50%. And then you can see after then a further 4 days, the quality goes up. It's very strange. And then goes down again, but the trend is of course to go down to nearly zero after nearly 3 to 4 weeks. So that's a taste. And also based on appearance, we do the image processing and also texture-based analysis. And also we check one of the spectral band data at 980 nanometers. That's minimum moisture content in the cake. That will show that for the vanilla cake, that's the trend for the change. And that's for chocolate cake. We do the same analysis. You can see for chocolate cake, we have a very high consistency compared with the automated analysis with the taste panel assessment. That shows actually the moisture in the chocolate cake has been analyzed more consistently using the hyperspectral camera than the vanilla one. But nevertheless, you can see that overall the trend is the same. That tells us actually that we can use the spectral camera to predict and the shelf life or the quality index of the baked products in this application there. So another application actually using this kind of a hyperspectral image, you can see that's a hyperspectral camera on the top. That's the meat samples. Actually, we did it in two different cases. One is we get data from the arbiter. Actually, while researchers visit the arbiter, setting up the system, we can see the whole animal which is get into the arbiter and then cut into pieces for imaging here. We then actually the process the meat and then analyze the data. Even cook the meat that include the lamb, the beef, and the pork, and then try to measure the freshness, the tenderness, the fat, the protein, the pH value, and the taste, as well as the moisture content within the meat samples. So that would be we also got a few projects funded by called the Quality Meat Scotland, and we also published a few papers on that one. If you're interested, you can go have a look. That's also show a very high level of consistency for meat analysis using the hyperspectral imaging sensors there. So we can have the eventually, especially for the freshness and the pH value. Fat protein is also the tenderness and also can be really very accurately measured using the spectral camera there. One more application we did actually we use now is analyze the Moscow melons using spectral camera to detect whether the sugarness of the melon, whether that takes a sweet or not. So unfortunately, you can see here we have to cut the melon into half rather than scan that one from the surface to outside. That's the limitation of the spectral camera. The Raman may be able to do a little bit better, although may still be a few limit depends on some bit itself. And here we show the three different kinds of the mannose here. We show that the red color is a high level of the sugar, and the sugarness, and the blue color is a much lower level of the sugarness. We can then realize that using that one data captured between 900 to 1700 spectral range. This is a system from Germany. It's called Red Air system from Inaugural. So we go this one to measure the sugarness on the surface. And then we can see the red color for this sample is particular. You can see the high level of the sugarness there. And then that will be almost no sugar. So what we can tell the kind of visualize the results. So that will be after we can do the prediction. We based on the data, and then we do a kind of regression model, predict exactly the level of the sugarness. And that including, I said, the 2D-dimensional image processing, spectral analysis, and also here, we also kind of post-process using the kind of mean filter, try to, or media filter to improve the performance there. That just managed to remove the noise on the detected results there. Because data itself, using pixel-based processing can be very noisy. And this is another example. Actually, we did is funded a Newton project. The Newton project with the Vietnamese government. So Vietnamese government involved that one, and the UK government support this one together. Use a hyperspectral imaging and try to do sorting of different rice seeds. We have different kind of rice. We want to keep the purity of the rice seeds and how to use that one. So actually, that's a simulation. We put the rice here, and then one of the rice looks quite different from this one. The other looks quite similar. We can see that's if we using the traditional way of the classification, that will be the result. You can see that can be very noisy. Most of the yellow here, a yellow can be also found here. Mix should be blue, but some classified as yellow. This should be red over here. This should be green, but some also be mixed classified. So you can see we can use the spatial color spectral. The classification actually only changed from 6% to 66. If we combine the color and the spatial or spectral and spatial, we can improve that one to 87%. Further, if we use that one with one of signal spectral analysis, that actually can be over 96%. So that shows how we can overcome the spectral noise, and then further combine the different features, the spatial features, and also the color or spectral feature together. Spatial feature will be the shape and the kind of measure of the contour of each image sample there. Yeah, that's one other application we did using called the format identification on the chewing gums. So that is a project funded by Johnson & Johnson, and you should know the name. It's an international big corporation. They're working on different areas. The food products is one of the major focus. And on the chewing gum, the format can be quite interesting. You can see that will be kind of dark or light hair. That's same as normal. And they also have something called a steel samples, metal or plastic. This will be beyond your imagination. Wow. Within the chewing gum, they go to this kind of samples. And then there will be something manually identified, and then try to see whether we can use a spectral camera detect that one from the sample there. What's happened from original image, the ground truth and the detection results there. I show that one. We use that one can help to improve. That's mainly for quality control or quality monitoring, because the product, for the product there, if the quality will not properly controlled, the whole batch may be rejected. Even that will be affected as export for the product export to some kind of a countries particularly in East Asia, such as Japan. So that's why they are very keen on to analyze the quality using the spectral camera there. So another interesting application we did with Scotch Whisky Research Institute. The whiskey actually in Scotland, that's a very, very important product, and just actually generates a huge value there. Then there's the revenue there, and you can see here the product, the whiskey was produced by major the malted barley. The malted barley, when the barley was malted, then the whole process that will affect a kind of a chemical compound called the phenolness or phenol level concentration. So traditionally, they need to send the samples to the wet lab to analysis that takes roughly 1 week or even longer time. And they would really want a more just efficient proper process. So that's why we suggest using hyperspectral image to image the samples and then to predict the phenol level concentration using spectral data. We also tried using a different kind of the bands, that's a band selection, to improve the prediction and to see how the phenol level concentration can be predicted. Yeah, so that will be also, I said, we've published quite a few papers in food chemistry and in some other, and that shows actually the different kind of the products and then how their concentration will change based on our process. And this shows how the number of the different bands, 55, 56, and then how the results will differ from each other. Yeah, and is another application also is about with linked to the Scotch whiskey. It's mainly called the peat analysis, because in the whiskey industry they use the peat actually to burn. So they burn the peat and use that smoke, try to affect the malted barley. That gives a particular taste of the whiskey product. Again, the peat itself contains different kind of phenol compounds as well. The common cell we are also asked to do a kind of analysis to see whether this may affect the overall performance. So we can see the peat samples here. We also have the condensate sample, that's a burn the liquid. So you burn the peat, they collect the smoke, and then just put in the water there. The water they contain that we call the condensed sample there. Then we try to measure the phenol concentration using the peat itself and the condensate. Then followed by, you can see that's the real system from the hydro system cover. You can see the very near infrared is about 400 to 1000, and the SWIR system is 900 to 2500. That's the spatial and the number of the bands. So that'll be number of the bands. That's a spatial resolution there. And then you can see we do the data acquisition, we do the data analysis, and then followed by, you can see that's a kind of it's a quite complicated kind of combine the kind of machine learning and the conventional image processing. Eventually, we can get on one way is a classification, and another way would be the prediction. We use, for example, the 335 the sample categories and their condensate sample. We use 5 to 10% of training. We are grading at different levels. That's a classification. 99.25, moisture estimation, and the organic matter estimation. It's over 99%. They're very, very high accuracy there based on this particular application. Yeah. Sorry. That's one should go to the previous page. I was wondering why this is missing. Let's show that's for the body analysis. You can see number of the bands and how we can the prediction, and then you can see how. So that shows just you can see the R square and also the root mean square, how the prediction, the measurement differs from the ground truth. That shows a very high level of the consistency. Although the data you can see was very unbalanced. You can see high level. That's the number of the bands, and then most of the data here is just a very rare. The data will be here. We're also using the hyperspectral to detect the listeria on the salmon fillets. So that will be another for quality analysis of the food. And again, that shows when actually due to the limited speed resolution, only the ppm is higher, you can detect them successfully. Right? But again, that shows the potential there. We also use that one for detection. We call the corrosion on metal samples. For example, we have different kind of the corroded the compounds. There you can see that spectrally they have some kind of a calculation. That's why we can use that one to measure the corrosion or detect the corrosion before they can be visually seen by now human eyes. That should there is an application with actually is a nuclear industry. They protect their nuclear waste. So that's the additive manufacturing. That's another application. We use that one for the additive manufacturing. They're using the metal powders to generate 3D printing components. For example, this will be different metal powders, and that's named differently. But their appearance all looks very similar. Sometimes they may be confused, like mixed together, and then will be cause kind of trouble of may affect the physical property of the printing the products. Then they would like to measure the quality there. So that's why we would like to detect if there's something that is mixed. For example, that's if we mix something like this, that's the dual classification, spectral-based classification. That's after mixture that one and shake them evenly. That's the prediction. We can detect that as low as 1% of mixture of the different kind of compounds here. So that will be this work is also published in IEEE Transcending Industrial Informatics. So that will be some kind of technology we use that one, realize the feature there as well. And we also apply that one for industrial automation, combine the hyperspectral imaging AI machine learning. For that, we can do the data process and data collection, followed by the feature extraction learning and machine vision. They can do classification regression of, for example, detect the defects, the scratch, cracks, contamination, and also adhesive the residuals, impact damage, or coating gradient on the fiber materials. It can be glass fiber or composite fiber material. This is a project funded by European Union. It's a Horizon 2020 project. It's 9.8 million euros. It's a very large project. We can show example here. You can see we can actually combine this one with a robot arm. That's why it's a KUKA robot. The sample can be put in. We just do the data analysis, and eventually you can see that will be what kind of damage on the surface. That's actually part of the car body, and what kind of interesting part we can detect that. So that shows a kind of interesting application as well. So short summary will be a hyperspectral imaging is a non-destructive technology which can be used for inspect in a wider range of the applications. The challenges there and for feature extraction, data reduction, so include band selection. So we propose a number of applications, the algorithm there, technology there. So if you're interested, you can go have a look. And the wider range of application I try to introduce for agriculture, food, drink, pharmaceutical, whatever. So that would be give you, I hope can inspire you guys and see if something would be of interest, we can maybe work together. So thank you, and a question.